All right, this video we're going to take a look at the population variance versus sample variance, and in particular why for sample variances we divide by n minus 1 as opposed to n, or even something like n minus 2. So I have a Jupyter notebook here, and I do have the code on my GitHub page. I might link that eventually here. But I'm going to import NumPy as MP and random as RD. So NumPy will allow me to do the calculations. Random will allow me to generate random values. So I'm going to walk you through the code here. So that way, if you want to try this out, you're free to do so. But population, we're going to generate 10,000 random integers between 1 and 100. And that'll represent our population, which is a fairly decent population of 10,000. And then I have these empty lists for sample 1, sample 2, and sample 3. Sample 1, I'm going to populate it with variances where I just divide by n for each sample. And then sample 2 will be variances where we divide by n minus 1 for each sample. And then sample 3 will be an n minus 2, just so you can see that one as well. So what we need to do is we need to populate each of these lists. So essentially what's going to happen is I'm going to put 10,000 items in each list. So that's what this range 10,000. So for underscore in range 10,000, so it means we're going to do the following 10,000 times. We're going to take a sample of these 10,000 integers between 1 and 100. So we're going to sample from the population. We're going to take 50 of them. So out of the 100,000, or the, out of the 10,000, we're going to take a sample of 50. Then what we're going to do is that sample, we're going to calculate the variance for with using n in the denominator. Then for that sample, we're going to calculate the variance where we use n minus 1 in the denominator, and that's what DDOF, I believe, stands for data degrees of freedom, is 1. And then we're also going to calculate the variance using an n minus 2 in the denominator. So n in the denominator for our sample, that variance, each of those are going to go into sample 1. N minus 1 in the denominator, each of those variances are going to go into sample 2. And then n minus 2 in the denominator, each of those variances are going to go in sample 3. And what we're going to see is the then we're going to take the mean of each of those lists. So again, in each one of these lists, we're going to put variances in them, and then we're going to find the mean of each of these lists. And what we'll find, excuse me, is that the mean with the variance with n in the denominator for the sample is going to underestimate what the actual variance of the population is. With n minus 1, it's going to be closer to what the actual population is. And with n minus 2, it's actually going to go above what the actual population is. And as far as n minus 1, that mean of this list, it could be below, it could be above, but it will be the closest of the three. So I'm going to have it print up the n in the denominator, n minus 1, and n minus 2 for each of the samples, and then also be able to tell what the actual variance of the population is. So let's give this a go, and hopefully it won't take too long. So it is doing quite a bit here, so it has to generate the 10,000 integers for our population, and then it has to sample 50 of them. Okay, so that didn't take too long. Okay. So using n in the denominator for calculating variances of our samples, we get a variance of 804.5865. Using n minus 1, we get 821.0066. And using n minus 2, we get 838.11095. So that would be the mean of each of the variances in our lists. And notice the actual variance of the population that we did way in the beginning here, calculating the actual variance of this entire population, is 821.368 roughly, which out of these three values, the one that's closest and pretty close, significantly close to it, is using the n minus 1 in the denominator for calculating sample variance. So in terms of targeting what the population variance is for samples, That's why we divide by n minus 1, because look at this value of 821.0066 compared to the actual variance of the population. So using n in the denominator, that value is typically less than it underestimates what this value is. And we can even, just for fun, use n minus 2 in the denominator, and that tends to overestimate. So using n minus 1 is kind of like that third bowl of porridge. It's just right. So, but hopefully this makes it a little bit clearer as to why dividing by n minus 1 when calculating sample variance is a closer approximation to the actual population variance than just, let's say, dividing by n or dividing by even n minus 2. So, all right, that about does it for this video. Thanks for watching. I'll see you next time.